everyone, welcome back to the channel. So in today's video, I'm going to be talking about how we actually come up with the exact number of permutations on a Rubik's Cube. So I'm sure you've all seen this a lot on my channel, and today we're going to talk about how you get, well, this number. So the first thing we're going to think about is an actual Rubik's Cube, right? So here's a cube, and like any other cube, this cube has 8 corners, 12 edges, and 6 centers, and that's just true for every single cube in the universe by definition. So what we're going to look at is, say you take, we're going to look at corners, and then we're going to look at edges. And one thing to note is that centers are always fixed with respect to each other and on the cube. The centers are always fixed in place, so it doesn't matter whatever I do with the cube, it doesn't matter. It does not make a difference to any of the centers. So let's start with the corners, shall we? So in terms of corners, there are 8 different places that a corner piece can go. And let's first talk about permutation, because that's a slightly more important concept to begin with. What are the different number of ways that you can put 8 different corners at 8 different spots in the cube? So let's just think about it as it's essentially a problem of permutations. So let's just say these are the 8 different spots, right? Now your first spot, you have 8 choices. All 8 corners are available to you. So for your first spot, you have 8 choices. Now, once you choose one of those, you've taken that out. So now you have 7 choices remaining. So for the next spot, you only have 7. Now you've chosen 2 corners, so you only have 6 remaining for the next spot, and so on. So as you get down to the last spot, you have only one possible choice for the last spot, right? Because there's only one corner left, and this makes sense. Now, the number of possible arrangements of corners in this sense is just a product of these numbers. And the reason for that is, think of it as if you have 3 spots and you have, say, A, B, and C. How many ways can you arrange A, B, and C in 3 spots? So say for the first spot, you can choose between A, B, and C. So you can put A there. And then there's 2, B, C, and C, B. So A, B, C, and A, C, B. And then you can put B there, and then there's B, A, C, and B, C, A. And then you can put C there, and there's C, A, B, and C, B, A. And so each of those has 2 others, and that's because once you set one of them, the next spot has 2 and the next spot has 1, and 2 times 1 is 2. And so for these 3 choices, you have 2 for each, so 3 times 2 is 6. And you can just extrapolate this logic to bigger numbers, to higher orders of combinations. So in this case, it's 8 times 7 and so on up to 1, which in math we just call 8 factorial. So great. This gives us the number of, nope, not orientations. It gives us the number of permutations that are possible for the corner pieces. So we've got that. That's great. But now let's look at orientation, which is how a corner is actually oriented within its spot. So as you would expect, each of the corners in each of the spots has 3 possible orientations. 1, 2, I shouldn't be doing this, but 3. And the other one is just back to normal. So there's 3 possible orientations. So logically speaking, so you pick one of these spots, it has 3 possible orientations. The next one has 3 as well. Just like how I twisted one of those, I could twist any of the others. The next one has 3, the next one has 3, and so on. But what about the last one? Because let's think about this. A Rubik's Cube is a problem in group theory, essentially. But it's also a problem that you can only solve by making changes to the group like this. And I'm sure there's a name for it in math, and if someone knows the math, please leave a comment down below so I can learn it myself. But you can only make moves like this. This is not a legal move to solve a Rubik's Cube, because you're literally just twisting a corner, and like by that logic you could just twist any number of corners. And so this in fact is not a possible state. So this means that the orientation of the last corner piece, you have 3 times 3 times 3, as we can see here. This has 3, this has 3, and so on, right? But for the last piece, it has to be dependent on the second last piece, or any of the orientation of the others, basically. And so there's only one possible orientation, because this is unsolvable, this is unsolvable, this is solved, but this is the only case that makes sense for an orientation of the other corners being all solved, right? So if I scramble the cube up completely, I did whatever, right? Now the corners are all like this. If I twisted one of these, this state is impossible to solve on the Rubik's Cube. And so is this. But this one is not impossible to solve, because I did not make any twists beforehand. There's no illegal transformations happening here, which means that this is how it works. And so for the last corner piece, it is dependent on the states of every one of the others. So you may have had the choice of 3 for every one of the others, but this last one, you don't have 3 choices. In fact, you only have 1. You don't even have 2, because it eliminates 2 of these 2, 1 and 2, these impossible choices, and this is the only one that works out. So for the last spot, you only have 1 choice, which gives you a total of 3 times 3 times 3, 7 times, because that's 7 times. And so you get 3 to the 7th power. And this is orientations. And now, just like the logic we used with the permutations, this means that the total number of possible states for a corner, for all the corners to be in a Rubik's Cube, is just a product of these. Why? Because for any one permutation, you can have any other set of permutations and any other set of orientations. So, for corners, the number we have is 3 to the 7 times 8 factorial. Hooray! So that's our first part done. We're building up the total number of possible permutations of the Rubik's Cube. Also, I should clear up at this point that the permutations I'm referring to right here for the corners are essentially how you would place the pieces, not how you would orient them in each spot. So just the number of spots. And when we talk about the giant number I showed you at the starting of this video, that is the total number of possible states, I should say states for that, of the Rubik's Cube. But colloquially speaking, we just call it permutations. So don't get confused with that. Anyway, let's move on to edges now, because we finished corners, we know centers are fixed. The only thing left is the edges. So let's move on to the edges. For the edges, we have 12 of them. And so we have a similar logic to what we had before. You have 12 spots. So let me just do this real quick. There's 12 spots. And so for the first spot, you can choose 12 different independent edge pieces. Now you've chosen one of them, so you only have 11 choices remaining for the next spot, 10 for the next, and so on. It's the exact same logic. And then the last spot, you only have 1, so you only have 1. So this, just like before, is just 12 factorial. And yeah, that is the number of permutations of the edge pieces. So that was pretty easy, right? I mean, now we know the logic, so it's pretty simple. It's the same thing for the orientation of the edges as well. But remember one thing, corners they share colors with 3 adjacent centers from 3 adjacent faces. But edges only share it with 2, because they're in the middle, right? They're not in the corners, but they're not on that side. So they only share it with 2, which means each edge only has 2 possible orientations. It could be like this or like that. And I won't take it out and put it like that because I do not want to abuse this cube anymore. Poor cube. So that means that for the 12 spots, the first one you have 2, the second one you have 2, the third one you have 2, and so on. But again, the last spot is the same logic. You cannot just have one flipped edge on the Rubik's Cube. So for example, let me solve this cube and kind of show you. Well, I'm not going to show you what it would look like, but I am going to show you what it's like, why it wouldn't work. Here's a solved cube, right? So if I took any one of these pieces and just flipped it in its place, there's no way you can solve that by making just turns of layers. You would have to remove it physically and put it back, which violates the idea of the Rubik's Cube being a closed group. And so the last piece is dependent on the orientations of all the others, and so that is 1 as well. So instead of 2 to the 12th, you would have 2 to the 11th power. And that is the number of orientations for the cube. And yeah, so at this point, using the same logic, the total number of possible states, so I should say corner states for before. And now the total number of possible edge states, similarly, is 2 to the 11 times 12 factorial. Edge states. And at this point, you might be wondering, well, that's just a solution, right? Because let's just recap that a Rubik's Cube, and this part might be blatantly obvious, is just a combination of the edges and the corners and the centers. So the total number of possible states of the Rubik's Cube is basically the total number of states of the edges, 2 to the 11 times 12 factorial, times the total number of states for the corners, which is 3 to the 7 times 8 factorial, times the centers, which we know are fixed. Like any of these moves is not going to change the positions of the centers. There's only 1. So this should just be my answer, right? And if you multiply these out, in fact, you get I will need a calculator for this one, so please bear with me while I do that. You get this giant number. So I hope I'm not leaking any personal information there. But anyway, you get this giant number according to Google, which is 8.56. Apologies. It's 8.65040007 blah 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 times 10 to the 19. Now, if you have a sharp eye with this, you may have noticed something. But it's fully fair if you haven't noticed it, because this is a very giant number and it's not something that's pretty obvious right off the bat. But the number I showed you at the start of this video was actually exactly half of this. Now, I'm not going to make that assumption to get to the result. I'm not going to say, oh, because it's half, we just divide by 2. No, that's not what's going to happen. But I will describe something else about the Rubik's Cube that you may not have considered, because quite frankly, it's something you do gloss over. Which is, so far, we've considered the corners and the edges to be separate entities. But there has to be a relation between the states of both, right? Because, for example, in fact, I'm going to take the cube apart just to show you. So after 2 minutes of painstakingly taking the cube apart just to do this, here's something interesting. If you notice, this cube is entirely solved except for these two corners. These are the only things unsolved, and they're just off by one swap. This belongs here, and this belongs here. So what do you think is the problem with this? Well, any transformation you make on the cube has to create more than one swap of any given type of piece. Like, I can't just have one edge swap or one corner swap. Why is that? Because let me try and solve this corner swap with an algorithm that we, in the cubing circle, call the T permutation, which basically swaps these two corners. It also does one more swap, which is what I mean, like it can't do just one swap. But let's see what happens. This is the T perm. And I have solved the corners, but I've swapped the edges. So and now here's the edges swap, right? Now I'm going to do something we call an H perm, which basically swaps these edges, but also swaps one more pair of edges. Cannot do the H perm. Let's solve those edges, but now these edges are unsolved. And now if I try to solve these edges, but now the corners are solved. Like, do you notice what's happening? The swap is just distributing itself across edges, or even if I try swapping these two corners, I tried solving them, I solved them, but now I have essentially swapped two other corners. What's happening here, right? There's no way to solve this. You might solve those two corners, you're always going to swap two edges. You might try to solve those two edges, you're going to swap two corners. There's no winning. And all of this is basically to say that there is no way for you to do just one swap on the cube. Now, think of it in the context of us arranging pieces, right? That's how we were calculating this before. We were going, okay, I have 8 choices at first, then I have 7 choices, then 6, then 5, then 4, and so on, right? By this logic, technically, for the last 2 parts where I had 2 choices and then 1 choice, those are kind of linked, okay? And if you think of it in terms of, let's just call one of the cycles where you put the pieces a certain way and you end up the right way every time. Let's just call that an even cycle, okay? And let's call the other type where you put all of the pieces, but you end up with this, an odd cycle. Now, in terms of assembling the cube, we're going through every possible state of this cube, right? Every single combination and permutation of pieces on the cube. But there is no possible place where you have just 2 edges swapped, or just, just 2 corners swapped, or just 2 edges swapped. These are impossible states. You basically cannot just have 2 choices for both. But there's one more thing. There's one more caveat. So here's the reason there's a caveat. So by this logic, I should just take this 2 and make it a 1. And I should take the 2 that's here for the edges and make that a 1. Which would mean I'm dividing by 2 there, dividing by 2 here. I should be dividing this by 4. But that does not exclude the case, which I'm going to show you now. So remember we had the 2 corners swapped. Here the edges swapped as well. And this is exactly the T permutation I referred to before. And this is what that does. This is solvable. The case where there were 2 corners and 2 edges swapped is solvable. So that means that I'm not exactly dividing by 2 for each of the parts, because there is one dependency where both swaps. So the first part removes one set of corners being swapped. The second part removes one set of edges being swapped. But by doing so, we are also removing the part that has both of these swapped, which means that we're not dividing by 4, because one of those is actually possible where both are swapped. And this is the T permutation. And so that means we're dividing by 2. Because instead of all the cases, half of them are possible, half of them are not possible. And so this number, this giant number right here, gets divided by 2. And the final answer that you get is exactly the number we know and love, which is, well, I'm not sure if we know or love this number, but the number is 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489,856,000. And that, my friends, is exactly how you arrive at the total number of states possible. I should say possible because this includes all of the stuff we just discussed. Means there are impossible states on the Rubik's Cube, right? So this is the total number of states possible on the Rubik's Cube. And that is the end. So we've derived this number. And you can do the math for yourself, like all of these weird looking symbols, these powers, these factorials. You can do all of them yourself. You will arrive at the same answer. And you can also notice kind of that these, like there's a times 2 dependency, like you can multiply our answer by 2 to get what we got before. And that's pretty cool. So yeah, this is how big. This is how many possible states there are on the Rubik's Cube. 43 quintillion. And even a 1,000 is huge, but even a million is huge. This is million, billion, trillion, quadrillion, quintillion, right? That's the order. That's how big this number is. So yeah, that's all for this video. Thank you so much for watching, and think about this. This is just a 3x3 Rubik's Cube. Take a 5x5. Imagine how many possible states there are on a 5x5. Heck, take a 7x7. Imagine how many there are in this, right? So as you go up this number goes exponentially higher. And that's the cool thing about Rubik's Cubes. It's all math. It's all math. You don't need math to solve it. Like, please, if you needed math to solve it, honestly, even I would not be that great at it, but you don't. You should learn how to solve it, in fact. But yes, this is the total number of permutations on the Rubik's Cube. Thank you so much for watching this video. If it was helpful, well, share it with your friends and let them learn how cool the Rubik's Cube actually is. So yes, thanks for watching, and yeah, take care. Peace. Yes, everyone, to confirm, this is the beginning, well, the second episode of a new series that I'm calling Continuum, and I think it's a cool name. I will explain more in the next episode of Continuum, so stay tuned to the channel.